In this session and the next few, we will explore the idea of a mole. A mole is a counting unit, a unit that chemists use very often, and that is why it is so important for us to use, because individual atoms, individual molecules or ions or formula units are extremely small, very inconvenient to actually work with. Therefore, chemists work with moles instead. Now, before we talk more about moles and try and figure out what is a mole and how to use that in calculations, let me ask you a very simple question. Have you ever gone to the grocery store to buy eggs? Hopefully your answer is yes. If not, if you haven't done it personally, maybe that can be your project for this evening, where you go to walk into the grocery store to buy eggs. Now, if you're talking about just a normal grocery store, I'm not talking about specialized stores where this may not work. In a normal grocery store, can you just walk out with one egg if that's all you need for your omelet? Or maybe how about three, just because I have three members in my family that each of them needs one egg? Can't do that. The grocery store insists that you buy the whole package that it sells the eggs in. In other words, whether it's a dozen or half a dozen, if they have half a dozen packet, or a couple of dozen packet if they have that, or whatever the packet size is. But you have to pick up that packet. Similarly, our mole is a packet. It is a packet of particles. Now, if you remember from our previous discussion in a previous session, we defined the term particles. We said that particles is a very general terminology which can mean a bunch of different things, and we'll talk about that again. But when we work with chemicals, whether they are elements or compounds, molecular compounds or ionic compounds, we work with packets. Yes, you can have a whole packet, in other words, a whole dozen of eggs, for example, or you can have half a dozen if the grocery store sells that, or you can have 1.5 dozen or 2 dozens, or if the grocery store is amenable to that, maybe a quarter of a dozen. In other words, you buy eggs in dozens, whether multiples of dozens or factors of dozens. Similarly, mole is our dozen. Mole is a dozen of for a chemist, of particles of a substance that we are working with. And that is, it's a packet of number of particles. Just as a dozen always implies 12. I mean, whether you buy, if you buy a dozen chicken eggs, that would be 12 chicken eggs. If you buy a dozen duck eggs, they will be 12 duck eggs. How about a dozen dinosaur eggs? Would be 12. How about dozen mole eggs? I mean, moles don't lay eggs, sorry. Ant eggs. I mean, they will be 12 ant eggs. My point being that as soon as the word dozen is used, the number 12 is implied. That there will be 12 of the items listed in that dozen. And then, of course, depending on your recipe, you could choose to use multiples of dozens or factors of dozens of eggs in your cooking. Similarly, depending on our need, we could either use multiples of moles or factors of moles in whatever it is that we are doing of the particles of the substance being used. Now, when we use the word particles, I need to specify this once again. The word particles is a very general word. This word could either be atoms if we are dealing with atomic elements, is a substance. It could be molecules if the substance we're working with is a molecular element or a molecular compound. But it could be formula units if you're working with ionic compounds, or ions if you're working with ionic compounds. So the word particles is just a general word which must be replaced by one of the specific words below, depending on the context. And I'll repeat this as we do problems in this concept. Okay, so as I said before, that since just as a dozen of anything implies 12 of that thing, similarly, moles of a chemical, of a substance, is a packet of that substance, of particles of that substance, of a specific number. And that specific number is 10.022 times 10 raised to 23 of those particles. You have to, this equation, this number needs to be memorized. Please, at all times, know that 1 mole excuse me, that 1 mole of any and every substance is 6.022 times 10 raised to 23 particles of that substance. Depending on the substance, the particles could either be atoms, molecules, formula units, or ions as the context. In other words, one packet, this is a mole if it has 6.022 times 10 raised to 23 number of particles of that substance. Please go ahead, pause the recording and try to write this number 6.022 times 10 raised to 23 in a decimal format as opposed to a scientific format. That'll kind of give you an idea as to how big the number is, therefore give us an idea as to how small individual atoms, individual molecules, formula units really are. This number 6.022 times 10 raised to 23 particles is called Avogadro's number. Now Avogadro's number is given a symbol N. N is not nitrogen. I mean, N in this context, uppercase N, in this context is not nitrogen. Uppercase N in this context is referring to the number 6.022 times 10 raised to 23 particles. In other words, when we say 1 mole of a substance, we are referring to N number of particles of that substance, where N is 6.022 times 10 raised to 23 of those particles. Now this equation right here is a standard equation. This equation is an equation that will never change. So you need to memorize it because this equation can be used as a conversion factor. Now notice, going back to the equation, please notice what are the two units that are being related to each other using this equation. Exactly, you have moles on one side and you have particles, which of course, as I've said many times already, particles could either be atoms or be molecules or be formula units, or in some cases also be ions. So these are the other units. So whenever you're dealing with any problem, any calculation that relates moles to some kind of problem, some kind of particles, then this standard equation would come into play. For example, in this question right here, in this question, the two units that are being connected to each other, and it is, please read that very carefully, we are being asked to calculate atoms of sodium in 3.95 moles of sodium. So if you really, if you look very carefully, what we are really connecting to each other is we are trying to convert moles. By the way, MOL is the same as writing MOLE. MOL is an accepted abbreviation for MOLE. Now please do remember, MOLE does not mean molecule. Molecule is the particle in a mole, so very different, but MOL and MOLE are definitely the same thing. So in this problem, we are being asked to convert moles of a substance, sodium, into atoms of sodium. In other words, the equation that connects these two units is 1 mole of sodium in this case equals 6.022 times 10 raised to 23 atoms of sodium. That is the standard equation that we will need in order to solve this problem. Okay, so let's set it up. Now, I will remind you of the problems that we solved in chapter 3 when we did dimensional analysis, the whole idea of converting one unit into another. That's the same kind of problem solving strategy that I will use, wherein I will start with what's given. In other words, what is being asked to be converted. In this case, we need to convert 3.95 moles of sodium using a conversion factor that comes from a standard equation. So in this case, the standard equation is the equation given. such that the standard equation is used such that the unit you want to you do not want gets crossed out, which is moles of sodium. So moles of sodium gets crossed out, and the unit that you do need is the one that's left with, in this case atoms of sodium. Then you put in the number from the standard equation, which says 1 mole of sodium, 1 mole of anything, will have 6.022 times 10 raised to 23 particles, which in this case are atoms of sodium. Instead of writing 6.022 times 10 raised to 23, you could also write uppercase N, because uppercase N, Avogadro's number, is equal to this number. When you calculate this out using a calculator, the calculator answer comes out to be 23.7869 times 10 raised to 23 atoms of sodium. Now this calculator answer, of course, is not, number one, is not in the standard scientific notation. So we do have to take care of that by moving the decimal point one place over, which will change the exponent as well. And number two, this answer is not accounting for significant figures. Please remember from previous sessions, conversion factors do not affect significant figures in your answer. In other words, the significant figure will only be affected by the measurements given in the problem. In this case, 3 significant figures. So if you rewrite this number in the correct scientific notation and round off correctly to 3 significant figures, the answer will come out to 2.38 times 10 raised to 24 atoms of sodium. Okay, so here's another problem in which we are being asked to calculate moles of benzene C6H6 from given molecules of benzene. So once again, please ask yourself, which are the 2 units that are being asked to be converted from and to? In this case, we want to go from molecules to moles. In other words, once again, the Avogadro's equation comes into the picture, which says 1 mole of every substance, no matter what that substance is, will have n number of particles. Particles in this particular case are molecules, because we are dealing with a non-acidic molecular compound. Okay, so now we set the problem up starting with the data given that needs to be converted, in this case 3.82 times 10 raised to 24 molecules. Please do not abbreviate molecules as MOLE or MOL. They are not the same thing. You have to write it out. C6H6 needs to be converted to. So molecules needs to go away and needs to be converted to moles of C6H6, so that molecules crosses out. 1 mole of every substance contains 6.022 times 10 raised to 23, in this case molecules. When you calculate this answer using a calculator, you will get 6.343407506 moles of C6H6. It needs to be rounded. In this case, it needs to be rounded to 3 significant figures, to 6.34 moles of benzene C6H6. So the equation, we can easily convert from moles of a substance to molecules of a substance by using the Avogadro's equation, which says 1 mole of each and every substance, no matter what that substance happens to be, will have 6.022 times 10 raised to 23 particles of that substance. Please remember that the word particles is a very general term which must be substituted for a specific terminology for the particles given the substance being used.